So welcome everyone to I think this is the fifth talk of the session of the Midwest Computability Seminar. Very, very glad to have Julia Knight here to talk about describing structures and classes of structures.
Well, thank you very much. What I'll talk about is almost entirely expository. Most of the results are other people's, but I'll mention collaborators, and also something that I'd like to do with collaborators. Okay, so what I'd like to do is talk about some basic notions. The talk will be elementary in this way, and the topics have to do with describing specific structures, and the Scott complexity is the notion, and then characterizing classes of structures, that's Borel complexity, and then classification problems, that's Borel cardinality is the basic notion. And I'll say something about the sort of slippery meaning of useful invariance. So structures are countable. They have universe omega. For some things, that doesn't matter, but let's assume that the structures have universe omega. The languages are countable, usually computable, and the classes consist of structures for a fixed language, and they're closed under isomorphism, modulo the restriction on the universes. So the formulas that seem to be useful for describing specific structures and also classes of structures are L omega 1 omega formulas. And these allow countably infinite disjunctions and conjunctions, but only finite strings of quantifiers. So here are some sample formulas. If we want to say of a real closed ordered field that it's Archimedean, we could use an infinitary sentence that says for all x, and then there's an infinite disjunction, that's ORs. So x is less than 1, or x is less than 2, or x is less than 3, ... And this big V is the disjunction, the infinite disjunction. And the next formula says of an element in an abelian group that it has infinite order. So we have to say that x is not equal to 0, and that x plus x is not equal to 0, and x plus x is not equal to 0. So there's an infinite conjunction, infinite ands. So for L omega 1 omega formulas, we don't have pre-next normal form. We can't, in general, bring the quantifiers to the front, but we can bring the negations inside. And this gives a different normal form in which complexity goes up with the alternations of disjunction exists and conjunction for all. So we can measure complexity of L omega 1 omega formulas in this normal form in a pretty natural way. So it's a little bit like pre-next normal form, but for this other normal form. So a formula is sigma 0 and pi 0 if it's finitary quantifier free. It's for a countable ordinal bigger than 0. Phi is sigma alpha if it's a countable disjunction of formulas with finite block of exists, and then something that's pi beta for some beta less than alpha. And a formula is pi alpha if it has the dual form. It's a conjunction of formulas that start with a finite block of for alls, and then something that's sigma beta for some beta less than alpha. I'll use a piece of further terminology. I'll say that a formula is d sigma alpha if it's the conjunction of something sigma alpha and pi alpha. So a pi alpha formula is equivalent to the negation of something that's sigma alpha. And this is really saying it's defined by something that's sigma alpha and not some other sigma alpha. So computable infinitary formulas are also useful, especially, I'll be saying, what does computability have to do with all this? So computable infinitary formulas are L omega 1 omega formulas in which the infinite disjunctions and conjunctions are over computably enumerable sets. To make that precise, we'd have to give some natural number names to the formulas, but I won't worry about that. So we'll classify these computable infinitary formulas as sigma alpha, computable sigma alpha, or computable pi alpha for computable ordinals alpha. And the computable infinitary formulas have the advantage over arbitrary ones that they seem comprehensible. The things that are infinite, they're in the dot dot dots. It's something that we know how to list. So for the two sample formulas that I had mentioned earlier, the sentence saying of a real closed ordered field that is Archimedean, that's pi2, and it's computable pi2. And the formula that says of an element in an abelian group that it has infinite order, that's computable pi1. We could write an example of a d sigma 2 sentence, computable d sigma 2, saying that a Q vector space has dimension n. And what we would say is for the sigma 2 conjunct, we'd say there is an independent n tuple. So there is a tuple, and it doesn't satisfy any of the linear combinations equal to 0. And then we'd also say, this is the pi2 part, that there doesn't exist an independent n+1 tuple. So the, let's see. So let's turn to describing specific structures. And there's an old theorem of Dana Scott saying that for each structure, countable, of course, there's an L omega 1 omega sentence whose countable models are exactly the isomorphic copies of our given, the structure we want to describe. So such a sentence is called a Scott sentence. And I'll indicate how Scott did this. So he first found a collection of formulas that define the orbits of tuples in the structure. So for each tuple, there's a particular formula that is satisfied exactly by the elements that are the tuples that are automorphic to the one we're trying to describe. And then once we have those formulas, say phi sub a is the formula that just defines the orbit of the tuple A, then we get the Scott sentence in the following way. We take the conjunction of sentences row A, one for each tuple. So row empty says, what are the one element extensions of the empty tuple? And it says what it says is that for each y, phi b is satisfied by some y, and for all y satisfies one of the phi b's. And similarly, for a tuple A, we describe row A describes the one element extensions of the tuple A, or of something that is in that orbit. So we say for all u in the orbit of A, for all single elements y, it satisfies one of the one element extension formulas, phi AB, and all of these formulas are satisfied. For each B, there is a y that satisfies that. And you, just while we're looking at this Scott sentence, the way Scott did it, we can see that if all the formulas phi A are sigma alpha, then phi would be, if gotten this way, it would be pi alpha plus 1. I'll mention an if and only if version that's more recent there, but this is something that we can notice already. And it tells us that the orbit complexity influences the complexity of the Scott sentence. So for complexity of Scott sentences, there's an old result of Arnie Miller. In fact, there's several results of Arnie Miller, but I'll just mention one of them. He said some things about what forms of Scott sentences are really possible. And one thing he said was if you have a sigma alpha plus 1 Scott sentence, and you also have a Scott sentence for the same structure that's pi alpha plus 1, then there's one that's d sigma alpha. And of course, if alpha is a limit, or no, this sigma alpha plus 1, the sigma alpha part is really a disjunction, and one of those disjuncts is satisfied, and then you get something pi alpha. There's a result of Montalban. So this is taking what Scott had done, but then getting the converse too. So Montalban showed that A has a pi alpha plus 1 Scott sentence if and only if the orbits of all tuples are defined by sigma alpha formulas. There's an effective version of that with Rachel Alver and Charlie McCoy. We looked at Montalban's result and said, well, if we had a computable pi alpha plus 1 Scott sentence, then the orbits would be defined by computable sigma alpha formulas. We don't get the converse of that. You can say some things in it, but we don't know exactly when you're going to get a computable infinitary Scott sentence of some particular form. There are some results of Alver and Greenberg and Harrison, Trainer, and Turetsky that give really precise results on the possible complexities of Scott sentences and say how they're related to the orbit complexity. And there are examples that illustrate things that weren't known to happen. It wasn't known before this paper, where there certain things could happen, and they sort of completed the picture. Whoops. So let me give an example of a Scott sentence, just one in detail. So suppose we're trying to describe the very familiar structure, the additive group of integers. And I claim it has a d sigma 2 Scott sentence, and that this is optimal, that there's not something simpler. Now, this doesn't mention computability, but the proof is computability. So for the Scott sentence, well, we just write down. We take the conjunction of a pi 2 sentence that characterizes the torsion-free abelian groups, and a pi 2 sentence saying that for any pair of elements, there's some single element that generates both. And then we take a sigma 2, so the conjunction of these is still pi 2. And then we take a sigma 2 sentence saying that there's some element x that's not divisible by any n, or any primes, we could say. Okay, so this is a Scott sentence, and it's optimal. And the proof that it's optimal involves index set calculations. So for a d sigma 2 set S, there's a computable sequence of groups, Gn, such that the nth one is isomorphic to Z, if and only if n is in S. And similarly, we could relativize to some x, and this is the basis of showing that the Scott sentence is optimal. So it's using computability, although the result doesn't look as if it's computability. Let me also say about free groups. Again, very familiar groups. So for n bigger than or equal to 1, the free group on n generators has a d sigma 2 Scott sentence. In fact, it's a computable d sigma 2 Scott sentence. But this is optimal. I mean, there isn't one that's simpler than d sigma 2. So to say what the Scott sentence looks like for n bigger than or equal to 2, we would take a pi2 sentence saying that for every tuple y, there's an n tuple x that generates y. And then we take a sigma 2 sentence saying that there is an n tuple x satisfying no non-trivial relations. So what it generates looks just like the free group on n generators. But somehow we'd like to say, this is the group we're thinking about. And what we say to get that is to say that for all n tuples y, there's no imprimitive n tuple of words that would take y to x. So I'll say what this means. So the primitive tuples of words are the ones that could take one basis to another. And Nielsen did a very detailed analysis of these. He described exactly what they were. And he showed that the set of primitive tuples of words is computable. So the primitive tuples of words, they're somehow reversible. And what he did was describe some reversible operations on bases. Switch the order of the bases. That was one of these. Replace one basis element by its inverse. Replace one basis element by the result of multiplying it by another basis element. Those were these primitive tuples are gotten by describing finite sequences of those. So the free group on infinitely many generators is also has a Scott sentence that we can describe it. It's pi4 and computable pi4, and it's not terribly hard. I won't describe exactly what it says, but it's also, we can show that it's optimal. That is, McCoy and Walbaum show that it's optimal, and they're like for the ordinary free groups, for the finite ones, the calculation, the showing that it's optimal, showing that the Scott sentence is optimal, uses an index set calculation. It's quite a delicate one for this pi4, but it is an index set calculation. So there are other familiar kinds of finitely generated groups that turn out to have d sigma 2 Scott sentences. And based on the known examples, Ho and I had conjectured that was true for all finitely generated groups. It's not so, but it had looked plausible for a time. I'll say a little bit more who showed it, who showed this. So the complexity of an optimal Scott sentence, we'd already seen that it should really be connected to the complexity of the orbits. And Montalban's theorem definitely says that there's a pi alpha plus 1 Scott sentence if and only if the orbits of all tuples are defined by sigma alpha formulas. And there's this effective version of it. So the proof of the non-obvious, here are the orbits defined, and now let's build the Scott sentence the other direction. Let's get the definitions of the orbits. So that for Montalban, it uses a technique of Mackay. model existence, but that can be done effectively. So for the Scott sentences for finitely generated structures, I'll return to those. Harrison, Trainer, and Ho show that there is a, well, first of all, they showed that a finitely generated structure has the d sigma 2 Scott sentence if and only if it's not self-reflexive, where that meant, so they gave the definition, that meant that there's no substructure B generated by a finite tuple such that the existential formulas true of the tuple in the original structure A are also all true in this substructure B. So Alver and Knight and Alver and I and McCoy showed that a finitely generated group has a d sigma 2 Scott sentence if and only if for some generating tuple the orbit is defined by a pi1 formula, if and only if for all generating tuples the orbit is defined by a pi1 formula. And Harrison, Trainer, and Ho had shown that there's a computable finitely generated group with no d sigma 2 Scott sentence. So they used the top result, but of course it's equivalent to this other. And so that ruined the conjecture, of course. It's still not known whether there's a finitely presented group that doesn't have a d sigma 2 Scott sentence. Harrison, Trainer, and Ho also looked at other finitely generated structures, and for fields, every finitely generated one does have a d sigma 2 Scott sentence, which is an interesting result. So let's turn to describing classes of structures and model. So the classes are subclasses of model. That's the class of structures with universe omega that have the language L. So fix the language and then look at the class of structures with universe omega for that language. So that's mod L. And we can identify mod L with Cantor space in a quite natural way. There are other ways to do it, but this is one. So for simplicity, I'm going to just assume that L is a relational language, but this doesn't matter very much. We could treat functions as relations of one higher arity. So let C be a set of new constants representing the natural numbers, and let alpha n be a list of the atomic sentences RA, where R is a relation symbol in L, and A is a tuple from C. And then we'll identify the structure A in mod L with the function in 2 to the omega, such that f of n is 1 if the nth sentence on our list is true in A, the nth atomic sentence, and 0 otherwise. So we're just giving the atomic diagram. So for Borel classes, let's recall what that means. We're thinking of classes in mod L, but of course we could identify them with classes now in Cantor space. And there's a natural topology on Cantor space generated by the Clopin sets that are the set of functions that extend a given finite initial segment. So if we're thinking mod L, all that's doing is deciding finitely many atomic sentences, of course. So the Borel sets are those in the sigma algebra generated by these basic Clopin neighborhoods. That is, we're closing under, well, we could say countable union and countable intersection, or countable union and complement, or countable union and intersection and complement. But since countable union and intersection are enough, we get the sigma algebra that way. Let's think of these things that way, and we'll think of the Borel hierarchy. So the Borel hierarchy goes this way for a countable, for a set is pi 0 and sigma 0 if it's a finite union of basic Clopin sets. In other words, if it satisfies a finitary, if we're thinking mod L, if it satisfies a finitary quantifier free formula sentence. And for a countable ordinal alpha bigger than 0, B is sigma alpha if it's a countable union of things, of sets that reach pi beta for some beta less than alpha. And B is pi alpha if it's a countable intersection of sets, each of which is sigma beta for some beta less than alpha. Oops. So now let's think about classes of structures and how to describe them, and recall some old results first. So Lopez Escobar showed that for a class in mod L closed under automorphism, it's Borel if and only if it's axiomatized by a sentence of L omega 1 omega. So this is one argument. L omega 1 omega is what we want to describe when we're thinking of countable structures. There's a finer result of Vaught that says for K in mod L, closed under automorphism, K is sigma alpha in the Borel hierarchy, if and only if it's axiomatized by a sigma alpha sentence of L omega 1 omega. Vaught's proof involved something he called Vaught transforms. And that always seemed mysterious to me. Michael Vandenboom, in his senior thesis at Notre Dame, gave an effective version of Vaught's theorem, which also yields, when you relativize it, Vaught's result. And Vandenboom's proof was different. I'll say something about it. Because again, it shows how computability and effectiveness methods add new information and new insight, even when the result doesn't mention computability. So let's see Vandenboom's results. So there's an effective Borel hierarchy. So the effective Borel sets are obtained from the basic Klober neighborhoods using CE unions and intersections. And they're each effective sigma alpha or effective pi alpha for some some computable ordinal alpha. Okay, so what Vandenboom showed is that a set B closed under isomorphism in mod L, of course, is effective sigma alpha, if and only if it's axiomatized by a computable sigma alpha formula. And similarly for the pi alpha and the formula, the sentence that's equal. The sentence, it's supposed to be a sentence, said formula, sentence. So this when suitably relativized, this gives Vaught's theorem, because of course the any L omega 1 omega sentence, any Borel set is effective Borel when you relativize to some x. So this actually does give Vaught's theorem, but let's see how did Vandenboom get this theorem. So we imagine building a generic copy of a structure A, an L structure, a structure in mod L. And the forcing language is propositional with propositional variables for the atomic sentences that might or might be true in the A star that we're building. And we have predicate formulas that define forcing for each formula in our forcing language. It says the formula would say we're forcing a certain sentence to be true if we map certain constants, they're going to be elements of our universe, to certain elements in the base structure that we're copying. And what these predicate formulas do, they do what the Vaught transforms did. But now, at least for me, it made sense, right? I could see, yes, I could see the proof, but I understood it after Vandenboom. Okay, so let me turn to Borel cardinality and classification problems. So Friedman and Stanley defined a way to combine, to compare the complexity of classification problems for different classes of structures, maybe in different languages. And their definition, they call it Borel embeddings. So a Borel embedding of one class in another is a Borel function from the one class to the other, such that the two input structures are isomorphic in the input class, if and only if their images in the output class are isomorphic. So we'll write K is less than equal B, K prime, if there is such an embedding. And we'll write strictly less if there's an embedding the one way and not the other. And we'll write equivalent if there are embeddings both directions. So the Borel cardinality of a class K is its equivalence class under this equivalence. So let's look at some of the classes that are on top under Borel equivalence. Classes of structures that are familiar, and most of them are sort of the familiar suspects that feel really complicated. So undirected graphs. I mean, you can do anything with an undirected graph. You can have all sorts of complexity of the orbits and all. And it's hard to describe all of these things. So it's not surprising that they should lie on top. Fields, they lie on top. Two-step nilpotent groups, they lie on top. That might be a little bit more harder to see. Linear orderings, they lie on top. Real closed ordered fields, they lie on top. There's a new result that it's in a paper on Math Archive that just went up a few weeks ago by Paolini and Schelach that says torsion-free abelian groups also lie on top. Sasha is interested in this, I feel sure.
Oh yeah, I am already Googling.
Okay, so let's look at the reasons for some of this, not all, but some. So the embedding, so how do we show that undirected graphs lie on top? We embed mod L for an arbitrary L in undirected graphs. And then of course, any class is a subclass of some mod L. Okay, so how can we get mod L? Well, we'll start with just an arbitrary binary relation and then modify. And the original embedding is due to Lavrov. It's his result. But there are other embeddings due to Marker and Nice and probably a dozen other people. And I'm actually going to follow Marker. It's the one that's given in his basic model theory book. So the embedding, it takes the first version, but I'll indicate how we modify it for mod L. So it's going to take a directed graph to an undirected graph. And there'll be a special point that represents each element of the input. And there'll be a special point representing each ordered pair in the input. And I have a picture that shows how the embedding works. So the input, let's give ourselves just 2 points of it, A and A prime. And here's a picture of the output that we might get. So they're the two special points, BA and BA prime, that represent the input elements A and A prime. And there's an ordered pair representing AA prime. And we connect it. We indicate, first of all, that BA and BA prime were representing input by connecting them to triangles. So that indicates your input points. You represent some input points. And then to say that we're representing an ordered pair. So we have, for the ordered pair with A first and A prime second, we have a point that's connected with just directly to A and with one stop to A prime. And for the other pair, A prime A, we have one stop from to A prime and we have no stops, that is, to go to A prime, and 2 stops to go to A. And then to indicate that in our input there was an arrow from A to A prime, we'll connect that special ordered pair point to a square. We'll make it a vertex of a square. And to indicate that there's no arrow going the other way, we'll put a pentagon to that other ordered pair point. Well, you can see how we can deal with more points. But also you can see what would we do if we had a bigger language? Well, we'd need some more n-gons, but more symbols. And we'd need more ordered pair points. And we might need more stops. If we have a triple, for example, we'd have the first component with no stops, second component, 2 stops, third component, 3 stops. But you can see it's an easy modification. So for this embedding, we can see a sort of easy way of actually defining the input structure in the output structure. In fact, we have existential formulas that say, or you're connected to a triangle that says you're representing an input point. And we can also say that there was an arrow by saying that the special point, the special ordered pair point, is connected to a square, is a vertex of a square. So it's an existential formula saying that. It's also an existential formula to say there was no arrow, because that was the pentagon. You said the special point is a vertex of a pentagon. So the input structure is actually definable by existential formulas in the output structure, and in a way that we could recover it computably. We could do the same thing if we have interpretations. For example, well, let me just say what is an interpretation, and I'll say something about examples. But so an interpretation of A and B is a sequence of formulas that define a set of tuples in B and relations on those tuples corresponding to the basic relations of A, and a congruence relation on the tuples, so that the resulting quotient structure is isomorphic to A. And for familiar examples, such that the interpretation of Z in N or Q in Z, because this could be the ring and the field. D had an arity. There was arity. In both of these examples, it was arity 2. But Montalban just defined a more general kind of interpretation for which the D didn't have to have an arity. And the formulas, well, instead of a single formula, you have a disjunction over all arities. But you could still have the feature that if the interpretation was defined by sigma 1 formulas, computable sigma 1 formulas, or sequences of computable sigma 1 formulas, then there was a Turing operator that took the copies of the B, copies back to A, to the input, recovered the input from the output. So let me mention another specific interpretation that helped put two-step nilpotent groups on top. So for fields, Friedman and Stanley gave a direct embedding of graphs in fields. Russell Miller and Hans Schoutens and Bjorn Poonen and Sasha Slapotok have a better one that gives you effective recovery. But Maltsev had one. Recovering the input structure took a couple of jumps. But anyway, knowing that we have fields on top, this puts this Maltsev embedding puts two-step nilpotent groups on top. So this embedding, Maltsev's embedding, takes a field to its Heisenberg group, where that consists of the 3x3 matrices with ones on the diagonal, zeros below, and then three other entries from the field. And what Maltsev did to show that this was one-to-one on isomorphism types, you could recover the field from the group, or from a copy of the group. He gave finitary existential formulas that define a copy of the input in the group, the input field in the group, but with an arbitrary non-commuting pair as parameters. And of course, that's enough if what you want to do is just recover a copy. You can find in your group somewhere a non-commuting pair. There is one. Find it, and then you apply Maltsev's definition. But we can actually do something a little better. So this is with Alver and Calvert and Goodman and Harzanov and Russell Miller and Morozov and Alexandra Soskova and Weishar. And it says there are finitary existential formulas with no parameters that for all fields effectively interpret F in H of F. And that gives us a way of recovering, of showing that the embedding is one-to-one on isomorphism types, but really Maltsev had already shown that. This gives us something a little more. So let me say a little bit about graphs in linear ordering. So Friedman and Stanley defined an embedding of graphs in linear orderings. And it's a bit complicated, so I'm not going to describe it. But the proof that it's one-to-one on isomorphism types does not involve a definition or interpretation, at least not of the usual kind. There can be none. So it looks as if just bits of the orbits are splattered all over, but they're there somehow. And in a sigma 1-1 way, you recover somehow. So for a graph G, let's let L of G be the corresponding linear ordering that from the Friedman-Stanley embedding. And what Harrison, Trainer, and Montalban showed, and also with Alexandra Soskova and Stefan Vodov, we showed that there don't exist L omega 1 omega formulas that for all graphs G define an interpretation of G in L of G. And this actually also used some computability. We looked at computable infinitary formulas and then computable relative to X. And we picked out some two specific structures that we, it couldn't work for both. So let me say something about some classes below the top. So the Q vector spaces, those lie below the top under Borel embeddings because there are only countably many isomorphism types. And there are some classes like graphs that have uncountably many, so that's easy. Subfields of the algebraic numbers, there are 2 to the L of naught of those, but there the isomorphism relation is Borel. And for some classes of structures, it's not. For example, for abelian P groups, it's not. For abelian P groups, well, again, that doesn't lie on top, but there's a subtler reason. I'll come back to it. It has to do with the kinds of invariance. How do you describe an abelian P group? You have to give the Elm sequence, and then maybe say something about the dimension of the divisible part. But for graphs, well, well, there are many more possibilities. So Kettridge had suggested that my students and I consider effective embeddings and effective analogs of Borel embeddings. And we looked at two notions, but one turned out to be more useful, I think, than the other. Sarah Quinn had said it was more useful to begin with when I was sticking with the other one, but she was right. So we defined for classes of structures closed under isomorphism again, a Turing computable embedding of one and the other is a Turing operator that takes k to k prime instead of a Borel operator, such that it preserves isomorphism. And we'll write k less than tc k prime if there is such a Turing computable operator. So the Borel embeddings of that were given by Friedman and Stanley and Lavrov and Meckler and Maltsev and Marker, the way they knew that these things were Borel is because they were actually computable. So we know there are lots of examples of computable Turing computable embeddings. For Turing computable embeddings, we have something nice. If we can describe structures in the output class, that tells us how to describe them in a nicer way than just saying, okay, here's the output structure, and that's how you describe that one. I mean, we always had that reduction. Once we embed one class in another, we can say about the input class, well, you're the one whose output looks like this. But what this pullback theorem says is if we have a sentence in the language of the output class, we can find a sentence in the language of the input class that's true in the input structures if and only if our original structure, our original sentence was true in the output. So, and these sentences have the same complexity. If one was computable sigma alpha, so is the other one. And the proof, again, is by forcing and using definability of forcing to get the pullback. Here's one example of using the pullback theorem. We can characterize the classes that embed in the Q vector spaces. They're the ones whose descriptions look like the ones for Q vector spaces, saying the dimension is at least such and such. So, and not at least such and such else. So for each sentence, each computable sigma 2 sentence that might be saying the dimension is at least n, the pullback is also a computable sigma 2 sentence. So let's return to abelian p groups just briefly. So there's a result of Fokina, well, joint with Fokina and Melnikov and Quinn and Safransky, that show that there's no Turing computable embedding of graphs in abelian p groups or in other classes of Ulm type. Well, the Ulm type came, the invariants sort of looked like the ones for the Ulm looked sort of like the Ulm sequence. And what we did to prove this was to apply the pullback theorem. And the way we defined Ulm type was it made this theorem true. We could apply the pullback theorem to it. And then results of Safransky let us generalize this to say, to get the result of Friedman and Stanley, there was no Borel embedding of graphs in abelian p groups. So let me say a little bit about invariance. So if we have a Borel embedding of one class in another, of course it reduces the classification problem for k to that for k prime. And having the same Borel cardinality really means having the same invariance. Now, what counts as useful is more vague. It's in the eye of the beholder somehow. So for Q vector spaces, dimension, we all accept that. Those are useful invariants. Abelian P groups, well, the Alm sequence plus the dimension of the divisible part. It's complicated, and it's especially hard to figure out what the dimension is, what the dimension of the divisible part is, looking at the group. But pretty much these are accepted as useful descriptions. For Boolean algebras, they're the Kettinen invariants, which I never thought. I thought, okay, give us the Boolean algebra if you want. It's the same. Kamerlin and Gauss say these are very complicated, but Kettinen did something with them, so that they have some use. But can you use it for something? I guess is the test. So for torsion-free abelian groups of finite rank, of specific finite rank, of rank n, what these look like, of course, is the subgroups of the Q vector space on, well, the Q to the n, the group Q to the n, with n z linearly independent elements. So think subgroups. So torsion-free abelian groups of rank n look like that. And Bayer gave invariance for the groups of rank 1. So he said, take a non-zero element, look at what prime powers divided or what natural numbers divide, and that's good enough. For different choices of A, you might get a different set, but the sets differ only finitely. So Bayer's invariants are based on this, and they're generally accepted as that's useful. So Maltsev and Kurosh gave invariance for rank n for n bigger than or equal to 2. And the idea was the same, looking at an independent n tuple and looking at the z linear combinations. There are infinitely many of those, of course. Say which n divide each of those. And the sets you get depend on the chosen tuple, but in a sort of predictable way. I mean, you can figure out. And but that's the basis essentially for Maltsev and Kurosh invariance. And as Hort and Thomas both report, Fuchs immediately dismissed these as no better than just giving us the group. So these I think are not generally accepted as useful. That's what Hort and Thomas both say. So what Hort and Thomas showed was that the Borel complexity goes up. The Borel cardinality goes up with the rank. And these results are very interesting, and they use a lot of descriptive set theory, and they use a measure, putting a measure on sets of groups. And that's sort of complicated. There's a result of Harrison, Trainer, and Ho that I'll mention. And it says that just that the class of torsion-free groups of finite rank lies on top under Borel embeddings among classes of finitely generated structures. Okay, so now I'll say what we'd like to do with Turbo and Russell Miller. So we'd like to see if we can use techniques from computability, things like generics, computable infinitary formulas, forcing copies, to simplify the results of Hort and Thomas in some way, or to look at the effective versions of them, where we have the Turing computable embeddings, to see if we can get simpler proofs of those. And we haven't succeeded, but we know a little, but we know some things about generics. But we'd also like, so for the Friedman-Stanley embedding of graphs in linear orderings, we'd like to show that there's no Borel operator that, given a copy of the output structure, the Friedman-Stanley ordering, recovers a copy of G. We think that's not possible. And finally, we'd like to look at the Paulini-Shelach embedding and show that it really looks, just from what I've looked at, so it looks like the Friedman-Stanley embedding of graphs and linear orderings. It looks to me as if the orbits are splattered all over the place, and not, and that we won't be able to have a uniform interpretation by formulas of L omega 1 omega. That it should be like the result with Vodov and Soskova. But we haven't done any of these. This is what we'd like. Thank you very much.
Thanks, Julia. There are questions?
Yeah, can I ask a question? And
Sure.
you of course know what I'm going to ask about. So Julia, did you actually like read the proof? Which looks pretty scary.
I've looked at it, but I can't claim to have chewed on it enough. Yes,
yeah, I just looked at it, and one of the definitions is pretty terrifying.
It's terrifying, but it's a construction that somehow reminds me of the Friedman-Stanley construction.
Oh yeah, so they kind of stretch it all over the group, and it's very hard to actually.
That's right. Yeah. So what should happen is it should be all these linear combinations. There are bits of divisibility. There are orbits coded in orbits.
This is pretty disappointing. I don't think it's going to be useful for us, right? So it's remarkable, but it's probably not very useful for us, right?
Well, I don't know. I mean, it might be useful.
We'll see.
Yeah, but I doubt that it's going to be an embedding where you actually see the relation somewhere or the operation somewhere.
Yeah, that would be remarkable, of course.
On
but
tuples that
who knows?
I think it's again, they're looking at finite tuples in the graph and coding them in lots of places. And that's what Friedman-Stanley did for the graphs in the linear orderings.
Yeah. Thanks.
Peter, go ahead. You have your hand up.
Yes, nice talk. In the beginning, you had this ordinal alpha measuring the complexity of a logical description of a structure in your language.
Yeah.
Now, in the examples you gave, the alpha involved is quite low. It was 2 or 4.
Yes,
So,
the examples I gave were simple.
Yes.
So if you look just at the computable ordinals, there the Scott complexity goes up with the ordinal. So you get arbitrarily large computable ordinals just from the for the Scott sentence for computable ordinals. There also carry Scott sentence, and the best Scott sentence has rank omega 1 CK plus 1 at the worst. So the Harrison ordering is an example of that.
So you have examples for arbitrarily large computable ordinals there.
Yeah, and also past the computable.
At which level, how far are the standard examples of mathematical structures which people actually are using? How high does those get into the ordinals?
Well, let's see. So I guess I'd have to ask what you're willing to count as
No, it's comparable.
We know there are fields that are pretty complicated, and we know there are groups that are pretty complicated. So various classes of structures include complicated ones.
So if you compare to the standard degree theory, there are natural examples at low levels, and by artificial means and iteration, we can construct them at arbitrary levels, but they are not taken very serious. Similar in complexity theory, you have in the Boolean hierarchy or the polynomial hierarchy, you have natural examples at low levels. At some point, it all becomes unnatural and artificial. I'm curious whether the same phenomenon holds for this kind of ordinal classification.
Yeah, eventually it becomes a matter of coding in a familiar class of structures, some graph or other, which is not terribly satisfying. I agree.
Okay, so you understand my intuitive feelings about these characterizations. Thanks.
Sure.
Yes. So I may have missed it, but your results on embedding into linear orders were specifically about the Friedman-Stanley embedding?
Yes.
I mean,
yes,
it seems unlikely that there should be a nicer one, but are there any results in that direction?
Nope. And that's a conjecture, of course, that in fact, I think we in the paper with Vodov and Soskovo, we conjecture that Friedman and Stanley did the best you could. But no, we don't know.
Thanks.
There are other questions? Maybe I'll just ask a quick one. This is something that I thought about a while ago, and I don't know if anybody has done anything like that, but if you look at the theory of broad reducibility, right, there are a lot of things that people look at beyond structures, right?
Sure. Oh, yes. You can, for
right.
sure.
Yeah. Have you looked at any of that in the context of these TC reductions?
So my focus being computable structure theory is no, but it certainly makes sense to look at arbitrary equivalence relations and compare them by Turing computable embeddings. Yeah. I haven't personally done it, but it definitely makes sense.
At a very low level, of course, the E0 relation, the finite difference relation, is exactly what classified the torsion-free abelian groups of rank 1.
Yep.
You were saying, basically. I don't know offhand of anything higher than that, but it's possible.
So are there other questions? If not, let's thank Julie again.
Thanks, Julia.